All right, let's dive into really cool AI stuff today. We got a research paper set. It's all about a new method called SEID.
SEDD.
Yeah, Score Entropy Discrete Diffusion, or SEFD.
Okay.
And this paper, Discrete Diffusion Modeling by Estimating the Ratios of the Data Distribution, it's saying SED could be a big deal.
How so?
Well, saying that it can help AI like really understand the connections between words, instead of just kind of putting them together one after the other, like a lot of language models do now.
Interesting.
Yeah. So let's unpack this, see why everyone's so excited about it.
Sounds good.
So the big thing with SED is that it's tackling the weaknesses we see in the typical language models out there, right?
Hmm.
So you've got models like GPT-2 that use what's called an autoregressive approach. Basically, they're predicting the next word based only on the words that came before.
Like writing a sentence one keystroke at a time.
Exactly.
Yeah.
It's like like writing a story, but you can only see the last sentence you wrote. Lose that big picture, that context.
Right. And that method has some problems too. It can be slow, it can make mistakes, and it really struggles to like fully understand the meaning of the whole text.
Definitely.
So to tackle this, you have diffusion models.
Diffusion models.
Yeah, they're already making waves in image generation. Like they're creating crazy realistic pictures now.
Wow.
So instead of directly creating the data, they add noise to it and they keep adding noise until it's totally random.
Ah.
And then they train a model to reverse that process, learning how to rebuild the original data from that mess of noise.
So it's like they're taking a clear picture, making it all blurry, and then training the AI to bring it back into focus.
Exactly. Now that sounds pretty complex.
It does.
But applying that to something as abstract as language, that's the real challenge.
Right, because words aren't like colors in a picture.
Exactly. Words are like individual units. You can't just blend them together the way you can with the pixels in an image.
Makes sense.
So previous attempts at language diffusion models, they had to use all these workarounds. And honestly, they couldn't really compete with those autoregressive models when it came to, how well they perform.
So is that what SEDD is doing? Bridging that gap.
That's exactly it.
It's going to do that.
The key is in something called score entropy.
Score entropy.
Yeah. So instead of trying to predict that noisy data directly, SEDD learns the ratios, like the relationships between the probabilities of different words.
Okay, back up a sec. Probabilities of different words.
Yeah. At each stage of that diffusion process, remember, we're adding noise and removing it.
Right.
SEDD is looking at how likely one word is compared to another. It's like figuring out the dance between words, how they relate and influence each other, not just their individual meanings.
So it's less about what comes next and more about getting the big picture, how each word fits into the overall meaning.
Exactly.
Got it.
And this leads to, well, quite a few advantages.
Like what?
Well, for one, SEDD just blows other language diffusion models out of the water.
Seriously.
Oh, yeah. It even goes head to head with those autoregressive models like GPT-2 and does just as well on those standard language tasks.
Wow. So it's a real contender.
Definitely. And the secret sauce is that score entropy.
So what you're saying is this score entropy, that's what makes SED so good.
You could say that. It helps SED create really good text, and it does it super efficiently. It doesn't need as much computational power or time to get to the same level of quality as something like GPT-2.
So it's faster and less resource intensive.
Mm-hmm.
That's huge.
Yeah, especially for like, those large scale applications.
Absolutely. So what else makes SED different? What else makes it stand out?
Well, think about it this way. Those autoregressive models, they're stuck generating text from left to right. That said, it has more flexibility. It can fill in missing parts of a text, using the context around it.
It's like it can complete your sentences or help you like brainstorm by filling in those gaps in your writing.
That's exactly it. Like having an AI writing buddy who gets your style and can kind of anticipate what you're thinking.
That's amazing. So how does it make sure the output is actually good, high quality?
Well, SEDD uses something called Twitty's theorem to get the best possible results during that denoising process.
Tweedy's theorem.
Yeah, it's kind of like a fine-tuning mechanism guiding the AI to create more realistic, more human-like text.
Got it.
Now, the paper does get to the specifics of how SED models that whole diffusion process.
Yeah, it looked pretty complicated. Can you break that down a bit?
Sure. They looked at two different approaches. They used matrices called uniform and absorb to represent how words change during the diffusion process.
Okay.
So uniform basically says any word can change into any other word.
Right.
With absorb, they added in this absorbing state where some words act as stop signals, kind of like how BERT handles things in language modeling.
So it's like experimenting with different pathways and rules for how the words are changed during that blurring and sharpening process, right?
Exactly.
And that affects the final text that comes out?
Yep.
Wow. This is a lot to take in.
It is, it's a lot, but it shows how much work is going on in this field. It's not just about finding one solution, but really getting into those nuances, seeing how different choices impact these AI models.
Yeah, for sure. It's like just scratching the surface, huh?
Definitely. But before we get, too deep in the weeds here, maybe we should think about what this means for our listener.
Good point. Why should they care about SED? What does it mean for the future of AI and all that?
Well, this research suggests SED could be the first real competitor to those autoregressive models. It could change the way we think about AI language generation.
Wow.
Imagine AI assistants that are not just faster and more efficient, but they get you, they understand your creative goals and can help you reach them in ways we haven't even thought of yet.
That's pretty mind-blowing. So we're talking about better chatbots that can have real conversations, AI tools that make us better writers, all because of this SED.
It's definitely possible, but to really get it, we need to dig deeper.
Deeper.
Yeah, the paper gets into the nitty-gritty of the math behind SED, how it all works on that fundamental level,
Okay.
and understanding that, that's how we'll truly grasp the importance of this new approach.
All right, let's do it. Let's get into that math behind SED. What are the key concepts we need to understand here?
Well, it all starts with score matching, which is a really important idea in diffusion models. So with score matching, the goal is to train a model that can really accurately estimate the score function of the data distribution.
Score function.
Yeah, think of it as like a map that shows you where the high probability regions are in your data.
Okay, so it's about figuring out like how likely different parts of the data are.
Exactly. And the score function, it describes the gradient of the probability density at a given point,
Grady?
like how steep the probability is changing at that spot. It works great with things like images where the data is continuous, and we can calculate those gradients smoothly.
Ah, so that's where the problem comes in with words, right?
Right. Words are discrete, they're separate units. You can't have half a word or blend them together like colors.
Yeah, that makes sense. So how does SED deal with that? How do you apply this score matching idea to words?
Well, they use this concept called concrete score. It's a way to generalize that score function idea, so it works for discrete data.
Okay.
Instead of gradients, it looks at the probability ratios between different states. So instead of asking how much is the probability changing here, we're asking how much more likely is this word compared to that word, at this point in the diffusion process.
So it's about relative likelihoods.
Yeah, exactly. How likely is this word compared to others as you're adding and removing that noise?
Gotcha. So where does score entropy come in?
That's how SED actually estimates those probability ratios. They came up with this new loss function called score entropy. And this function, it's got some really cool properties.
Like what?
Well, first, it's consistent. If you have enough data and your model is powerful enough, it'll eventually get to the true probability ratios. It'll zero in on that perfect understanding of how the words relate.
So it's reliable.
Mm-hmm. And it gets around some of the problems other methods had with discrete score matching. Like it handles the fact that probabilities can't be negative. Some of the old methods struggled with that.
Ah, so it keeps everything mathematically sound.
Exactly. Another thing is scalability. That score entropy loss function, it's designed to be efficient, even with tons of words and those really complex language tasks.
Which is important with language, right? There's so many words and ways to use them.
Exactly.
Now, I remember the paper also talked about something called Tweedy's theorem being used to make the text generation better. Can you explain how that works?
Sure. Tweedy's theorem basically gives you a way to ultimately denoise the data at each step as you're going through that reverse diffusion process.
Okay.
It's like a guide for how to go from a noisy, blurry representation to a clearer one in the most effective way.
So applying that to language, it's like a roadmap for choosing the right words as you're going from that random mess to a coherent sentence.
Exactly. And the cool thing is how they adapted Tweedy's theorem to work with words. Because remember, it's not like gradually sharpening an image. With words, you have to make specific choices at each step.
Right. It's not continuous.
Right.
You have to pick the right word out of all the possibilities. So they tweaked Tweedy's theorem so we could guide the AI in making those right choices as it goes through the reverse diffusion process.
Exactly.
That's amazing. It's like they took this concept from the world of images and found a way to make it work for language.
Yeah, and that's what makes this research so groundbreaking.
right, let's dive into some really cool AI stuff too.
Oh, hey, our listener wants to join in. What's up?
It seems that the entropy loss is the key to this diffusion model for the language. Can we wrap up the main takeaways for some key points?
Okay, let's tackle both of those.
Good idea.
So regarding cross entropy, the paper introduces score entropy as a novel loss function.
Right, and it's designed to extend score matching to discrete spaces.
Score entropy builds off of the Bregman divergence.
Exactly, and it generalizes standard cross entropy to general positive values.
Okay, so now let's wrap up some key points.
Sounds good.
Well, it's saying that it can help AI really understand the connections between words.
What's fascinating here is how it differs from just stringing words together.
Yeah, instead of just kind of putting them together.
Like those autoregressive models do.
Right.
So the big thing is that SED tackles the weaknesses in typical language models.
Exactly.
So models like GPT-2 use that autoregressive approach.
Predicting the next word based only on the words that came before.
Like writing a sentence one keystroke at a time.
Exactly.
Yeah.
So it's like you're writing a story.
You can only see the last sentence you wrote.
Right.
You lose that big picture, that context.
Right.
And that method has some problems too.
What kind of problems?
It can be slow and it can make mistakes.
Yeah.
And it really struggles to like fully understand the meaning.
So to tackle this, you have diffusion models.
Diffusion models.
Yes.
And they're already making waves in image generation.
No.
Oh yeah. They're creating crazy realistic pictures now.
Wow. How?
So instead of directly creating the data, they add noise to it. They keep adding noise until it's totally random.
Okay.
Then they train a model to reverse that process.
Rebuild the data?
Yeah, learning how to rebuild the original data from that mess of noise.
So it's like they're taking a clear picture
Making it all blurry.
and then training the AI to bring it back into focus.
Exactly. Huh. Now that sounds pretty complex,
It
but
does.
applying that to something as abstract as language,
No.
that's the
Yeah.
real challenge.
Right. Because words aren't like colors in a picture.
They are, words are like individual units. You
Yeah.
can't just blend them together the way you can with pixels.
Makes sense.
So previous attempts at language diffusion models,
Oh.
they had to use all these workarounds.
Ah.
And honestly, they couldn't really compete with those models.
They couldn't.
Not when it came to how well they performed.
So is that what SEDD is doing, bridging that gap?
Precisely.
How does it do that?
Key is in something called score entropy.
Score entropy.
Yep. So instead of trying to predict that noisy data directly,
Okay.
SEDD learns the ratios, the relationships between the probabilities.
Of different words.
Yeah. At each stage of that diffusion process, remember.
Noise.
Where we're adding noise, then removing it.
Right.
SEDD is looking at how likely one word is compared to another.
Oh.
It's like figuring out the dance between words.
So it's less about what comes next.
And more about getting the big picture.
Right.
How each word fits into the overall meaning.
Got it.
And this leads to quite a few advantages.
Like what?
Well, SEDD just blows other language diffusion models out of the water.
Seriously.
Oh yeah, it even goes head to head with those models.
Like GPT-2.
And does just as well on those standard language tasks.
Wow. So it's a real contender.
It is. And the secret sauce is that score entropy.
You're saying score entropy makes SEDD so good.
Exactly. It helps SEDD create really good text.
It does.
It does it super efficiently. It doesn't need as much power.
So it's faster and less resource intensive.
It is,
That's huge.
especially for those large scale applications.
Absolutely.
So what else makes SEDD different?
Anything else?
Well, autoregressive models generate text from left to right. SEDD, it has more flexibility. It can fill in missing parts, using the context around it.
So it's like it can complete your sentences.
Or help you brainstorm by filling in those gaps.
Oh, that's amazing.
So SS uses Tweedy's theorem to get results.
During that denoising process.
Yeah, it's kind of like a fine-tuning mechanism.
Guiding the AI.
Yep. To create more realistic, more human-like text.
Got it.
Now, the paper gets into the specifics of how SED models.
Yeah, pretty complicated.
They looked at matrices called cariform and cabsorg.
Okay.
So cariform basically says any word can change.
Any word.
But with cabsorb, they added in this absorbing state.
Gotcha.
Where some words act as stop signals.
Right.
Kind of like how BERT handles things in language modeling.
So different pathways and rules for how the words change.
Yep.
Affects the final text.
Yep.
This is a lot to take in.
It is. It shows how much work is going on in this field.
Yeah.
Not just finding one solution, but really getting into those nuances.
Yeah, for sure. This is like just scratching the surface.
Definitely.
Maybe we should think about what this means for you.
Why should you care about SEDD?
Good question. What does it mean for the future of AI?
This research suggests SID could be the first competitor.
Really?
It could change the way we think about AI language generation.
Wow.
Imagine AI assistants that are not just faster. They understand your creative goals and can help you.
Mind-blowing.
So better chatbots that can have real conversation.
Wow.
AI tools that make us better writers, all because of SEDD.
Definitely possible. But to really get it, we need to dig deeper.
The paper gets into the nitty-gritty of the math behind SED.
Okay.
And understanding that, that's how we'll truly grasp the importance.
All right, let's do it. Let's get into that math behind SED.
It all starts with score matching.
Score matching.
A really important idea in diffusion models. With score matching, you train a model.
Accurately estimate the score function.
Yeah, think of it as a map.
Gotcha.
It shows you where the high probability regions are in your data.
So it's about figuring out how likely different parts.
Exactly. And this score function,
Gradient,
it describes the gradient of the probability density.
works great with things like images.
The data is continuous, and we can calculate gradients smoothly.
So that's where the problem comes in with words, right?
Right. Words are discrete. They're separate units.
Yeah, that makes sense.
So how does SEDD deal with that?
Apply the score matching idea to words.
Well, they use this concept called concrete score.
Okay.
It's a way to generalize that score functional idea.
Relative likelihoods.
Yeah, exactly. As you're adding and removing that noise.
That's
how SEDD estimates those probability ratios.
They came up with this loss function.
And this function, it's got some really cool properties.
Like what?
First, it's consistent.
Reliable.
And it handles the fact that probabilities can't be negative.
Ah, so it keeps everything mathematically sound.
Exactly. Another thing is scalability.
Important with language.
Exactly.
Now, I remember the paper also talked about Tweedy's theorem.
Sure. Tweedy's theorem basically gives you a way to optimally denoise.
As you're going through that reverse diffusion process.
Exactly. And the cool thing is how they adapted Tweedy's theorem.
It's not like gradually sharpening an image.
With words, you have to make specific choices.
Gotcha.
Exactly.
That's amazing.
They combined ideas from different fields.
They did?
And that led to some really interesting results.
How did it stack up against the competition?
They tested SED on 3 standard benchmarks.
Okay.
The results were really impressive.
Wow. So it's actually surpassing the existing models.
And on the 1 billion words data set.
Holding its own.
And the results on those GPT-2 zero-shot tasks.
Generalized to new situations.
They did really well.
Incredible.
They also looked at how good the generated text actually was.
Comparing to GPT-2, what did they find?
They consistently produced text that was coherent.
Sensible.
Exactly. They also tested SL on this task called infilling.
Flexible.
Definitely a step forward in AI language generation.
But it's still early days.
True.
Lots of potential.
Definitely. We need more research.
Improve SED or more research?
One area is exploring different noise schedules.
Interesting.
Looking at different weighting schemes for score entropy.
Making it even more sensitive to certain nuances.
Exactly. We could explore using SED for all sorts of language tasks.
Like translation.
Dialogue generation.
I'm eager to see where all this goes.
Agreed. What are the key takeaways?
What should you be thinking about?
Well, SEDD is a real breakthrough.
Breaking through.
Teaching AI to really understand the nuances of language.
More efficient.
Exactly. It opens up possibilities.
They're pretty exciting. But we also have to remember
Lots of work to be done.
potential for making SED even better.
Exactly. Applying SEDD to other language tasks.
Beyond language model.
Think about things like translation.
Wow.
And it's all possible with SEDD.
Gotta be realistic too, right?
Absolutely. We have to make sure that SED is used responsibly.
Misinformation or harmful content.
We need safeguards in place.
Make sure that AI is a force for good.
Transparency.
It's a big responsibility.
Considering the ethics and working together.
Well, I think that's a great place to wrap things up.
Hope this gave you a lot to think about.
Keep learning, keep asking questions.
Just the beginning.